Let's turn our attention now to section 9.4, and we're talking about the comparison tests. The comparison tests allow you to compare the results of one known series to that of another series that is related. Here we're going to formally state and prove the direct comparison test. However, in essence, what the direct comparison test can be thought of is if you have something that's smaller, if you have something smaller than something that is already small, then that first one must be small as well. If something is smaller than something that is small, then that first one must be small as well. If you have something larger than something that's already large, the other one must be large as well. That's what the comparison tests essentially boil down to. But now, formally, we have the following theorem. So we have, let's begin with a couple of series. One is the sum of terms a sub n, and the other one is the sum of terms b sub n. Now, we're going to let all of these be positive, and we're going to let it be such that the nth term of a is always less than or equal to the nth term of b for every natural number n, for the first one, for the second one, for the third one, and on forever. If that's the case, then if the sum of bn terms converges, then the sum of the an terms also converge. On the other hand, if the sum of an's diverges, then so does the sum of bn's. All right? The proof of this, we can start off by looking at just that first statement. Assume that this sum converges. The sum as n goes from 1 to infinity of b sub n converges. And if it converges, well, it should converge to something. So let's say it converges to a real number L. Okay. Well, now we can consider the partial sums of this series. So let's let S sub n equal to a sub 1 plus a sub 2 plus a sub 3 plus ... all the way until you get to a sub n. And here that's the partial sum. The partial sum of this infinite sum. Okay, well now if that partial sum is defined for this, notice that because every one of our a sub n terms is less than every one of our b sub n terms, then adding up the a sub n's must give me something that's less than if I added up the b sub n's. Oh, but I know what happens when I add up all the b sub n's. I get L. Since my a sub n is less than or equal to b sub n, then S sub n is less than L, but since it's greater than or equal to 0, we know that the partial sums has to be greater than 0. All right? So that means that it's bounded on both sides. We know for a fact that the nth term of the partial sums is bounded. So that means that the sequence of partial sums is bounded. Okay, but if the sequence of partial sums is bounded, that's half of what we need for convergence. The other half would be if it's monotonic. But of course it is monotonic because look, all of these a sub n's are positive. So also, since a sub n is positive, or equal to 0, that we began with that assumption, then that means that every time you add another term, you're either adding 0, which means it's staying the same, or you're adding a positive number, which means the partial sum is growing. So also, since a sub n is greater than or equal to 0, this means that if you start with S1, that's going to be less than or equal to S2. Because once you add the second term, it's either going to stay the same, because it was 0, or it grew because it was something more than 0. But then if you add another term, s sub 3 will be bigger than or equal to s sub 2, and s sub 4 will be bigger than or equal to those, and s sub 5 will be bigger than or equal to those, and so forth. So here this is monotonic. So the sequence of partial sums is monotonic. I keep switching back and forth between capital N and little n. Is monotonic. So the sequence of partial sums is bounded and monotonic, so it must converge. But if the sequence of partial sums converge, by definition, that means the infinite series converged. But since that infinite series was just the sum of a's, then that means that I'm going to end up with the sum as n goes from 1 to infinity of a sub n converges. Just like that. All right, so this proves the first part of our theorem. If b sub n converges, we assume that, then that results with a sub n converging. Okay, so that proves that first part. The second one is logically equivalent to the first. Here, if this happens, then this happens. It's guaranteed. If this happens, this must happen. Oh, well, if this didn't happen, that means this one didn't happen either. Oh, well, if this didn't happen, that means that a sub n diverges. Well, then that must mean this didn't happen either. So if this doesn't happen, that means b sub n's series also diverges. So here the second statement is equivalent to the first. If the first thing happens, then the second thing must happen. Oh, but the second thing didn't happen. Oh, so it must have been that the first one didn't happen either. And that's the second statement. And that concludes our proof. So this is called the direct comparison test. The direct comparison test allows you to compare the terms of a series, and if they compare in this form, then you can say one converges forces the other one to converge, or the second one diverging forces the second one to diverge. You have to be careful with that direction though. So here, this is called the direct comparison test. And let's take a look at some examples of how that's used. So let's consider a series, the sum as n goes from 1 to infinity of 1 over the square root of n to the third plus 1. And the question is, does this converge? All right, now this one really looks like a p-series. Because look, I have a square root, which I can think of as a 1/2 power. So here this is n to the third to the 1/2 power. Well, that's n to the 3/2 power. That looks so much like a p-series. Oh, but except for that plus 1. And remember, when we saw p-series in a previous section, we were adamant that the p-series must be a constant over n to a power. This denominator should not have any pluses, minuses, or anything else. It should just be n to a power. So this extra plus 1 keeps this from being a very simple, easy problem that I could do. Well, yeah, but if that's the only thing keeping it from being easy, how do I get rid of that? Well, you don't get rid of it. What you do is you compare this to the one that you wish it was. To use the comparison test, what you want to do is you want to look at whatever series you have, look at its nth term, and see if you can't recognize another kind of series that has a similar nth term. You would want to say, oh, this really looks like a P series, except for this. Or this really looks like a geometric series, except for this. Or this really looks like a telescoping series, if it wasn't for this part. If that's the case, that's what you want to compare it to. It's not guaranteed to work, but it's a very, very good start. So here, I notice that this looks like a P series. This looks like the P series with P equal to 3/2. Power 3, but then the square root makes that 3/2. Oh yeah, but that plus 1's in the way. Okay, so now let's compare these two sets of terms. Let me compare the nth term of what I have, like this, with 1 over n to the third square root. This would be the P series that I want, okay? Or rather, this would be the nth term of the P series that I want. Okay, well notice here, this one has a slightly bigger denominator. This has an extra plus something in the denominator where this one doesn't. So if the denominator is bigger, that means the entire thing is smaller. Okay, so this nth term is smaller than or equal to this nth term. But if this nth term is always smaller than this nth term, then that means that adding these up will make it so that these are going to be bigger when I add them up. Or in other words, the sum as n goes from 1 to infinity of 1 over the nth over the square root of n to the third plus 1 is less than or equal to the sum as n goes from 1 to infinity of 1 over n to the third square root. Oh, but this I know converges. This converges because it's a P series with P, which is equal to 3/2, which is certainly greater than 1. Okay, so now this series that I want is less than this series that I know converges. Well, notice, if the one that I want is less than the one that converges, then the one I want must also converge. Intuitively, what this says is, okay, this must be smaller than this, but this is small enough to converge. It's small enough to give me the number 20 or the number 5 or the number something. It's going to converge. Oh, well, if this is small enough to converge, and this one's even smaller, well, it must also be small enough to converge. So, by our comparison test, our series converges. Does the series converge? Yes. The series converges by a direct comparison. That's the kind of test this is. This is a direct comparison with a P series that has P equal to 3/2. And that would be a complete answer. And let's see that again. Does this converge? We're going to take the sum as n goes from 0 to infinity of 4 to the power n over 5 to the power n plus 6. You can tell I work really hard for my examples. 4, 5, 6. Huh? So now this, go ahead and give this a try. Pause the video and see if you can't find something to compare this to. Remember, what you should do is try to find something that this looks like if it wasn't for this one thing. All right? Once you find something to compare it to, go ahead and perform the comparison test and see if you can confirm whether this converges or diverges. Once you've gotten an answer, go ahead and unpause the video and we'll go through it together. All right, this really looks like a geometric series because this really looks like 4/5 to the nth power. But this extra 6 gets in my way. Okay, well, let's get rid of that extra 6 there. I say, well, you can get rid of it? Well, no. But we can compare it to something that doesn't have it. Here, let's take 4 to the power n over 5 to the power n plus 6. We note that that's going to be compared to 4 to the power n over 5 to the power n, because that would be 4 over 5 to the power n. But notice this has a bigger denominator than this one does. It has an extra term. Oh, well, if that's a bigger denominator, that means the whole thing must be smaller. Oh, but if that's smaller, if the nth term is smaller, that means that the series that's made up by adding up these nth terms must be smaller than the series that's made up of these nth terms. After all, that is 4/5 to the power n. But this is a geometric series. Notice I have a, which in this case you could just have the number 1, right? That is 1 times 4/5 to the n. A is equal to 1, and r is equal to 4/5. Now remember, with a geometric series, if your r has an absolute value that's less than 1, then your series converges. Since the absolute value of r, which is the absolute value of 4/5, is less than 1, this is a converging geometric series. But again, this thing is small enough to converge, and this thing is even smaller. So if you're smaller than something that was already small, you must be pretty small yourself. So here, if this can converge, and this is less than term by term, then the sum of these terms must also converge. So here, does this converge? Yes, this converges by a direct comparison with a geometric series that has r equal to 4/5. Just like that. Now you have to be mindful of this direction. Notice, we're going to do one more example. And in fact, I'm going to take this same example here, and I'm going to change it ever so slightly. And by changing it ever so slightly, we'll realize that we have to be very careful with this direct comparison test. So consider the series n goes from 0 to infinity of 4 to the power n over 5 to the power n plus 6. But now instead of saying plus, let me go ahead and make this a minus. All right, so 5 to the power n minus 6. All right, well, that still really looks like a geometric series. It still looks like 4 over 5 to the power n. So I figure, okay, I'll still go ahead and compare that. All right, so that's going to be 4 to the power n over 5 to the power n minus 6. And I'm comparing that to 4 to the power n over 5 to the power n. Notice this denominator is smaller because you're subtracting something that you weren't subtracting over here. Okay, so since the denominator is smaller, that means overall this whole thing is bigger. Okay, so if these terms are bigger, that means that adding up these terms will give you a series that's bigger. Okay, so the sum as n goes from 0 to infinity of 4 to the power n over 5 to the power n minus 6 must be greater than or equal to the sum as n goes from 0 to infinity of 4 to the power n over 5 to the power n. Okay, and just like before, this is a convergent geometric series. And that doesn't help us at all. Think about that for a minute. Pause the video if you have to and try to think about what's gone wrong. Go back to your theorem and see what the conditions were. Look at this and try to think about it in terms of an inequality, what is greater than what. And once you think you figured out what's wrong, go ahead and unpause the video and we'll go through it. Notice this is convergent, which means it's equal to a number. this will equal to, I don't know, 7 or 45 or whatever. It's a geometric series, so I actually could go through and figure out what it's equal to, but it doesn't matter. It's a number. Okay, well then this is going to be greater than that number. Okay, so if this is the number 5, this could be the number 10, or the number 25, the number 400. But you know what else is greater than the number 5? Infinity. This is bigger than a finite number. There's a bunch of things bigger than a finite number, including something that's infinitely big. So here, if you are smaller than a finite amount, if this is a number and you are less than that number, then you must be a number yourself. But if you are larger than a number, well, you might be just a really big number, or you might go off to infinity. So here, the direct comparison test fails. That doesn't mean we found that this diverged. Maybe it does diverge, or maybe it does converge. When we say a test fails, that means it didn't succeed at its goal. It didn't tell us whether or not the series converged or diverged. So here, the direct comparison test fails, and we do not know if the series converges or not. All right. So the direct comparison test is a very nice and very powerful way of simplifying the nth term. If you have something that almost looks nice, you can compare it to the one that does look nice. But you do have to be mindful of your inequalities. The inequalities do have to fit this way. If a sub n is less than b sub n, b sub n converging makes a sub n converge. A sub n diverging makes b sub n diverge. But the other way is not true. If a sub n converges, that doesn't say anything about b. And if the series of b sub n's diverges, that doesn't say anything about the series of an's. So just be mindful of that. When using the direct comparison test, do be careful making sure that the inequalities are in the direction needed for the direct comparison test. So now you say, okay, well then unfortunately that just means that this one we can't really do, right? Well, no. That just means you can't do it by the direct comparison test. The other kind of comparison test that we look at is called the limit comparison test. And so we have a theorem. This theorem is called the limit comparison test, and it states that if you have a series of terms, all of which are positive, so let's start with that. Let a sub n be positive, and let b sub n also be positive. And, let be such that the limit as n approaches infinity of the quotient of these numbers is equal to L, which is just some finite number. That's some real number, where L is positive and finite. Or in other words, L is not 0 and it's not infinity. It's some number between 0 and infinity. So here, let me just say L is in the interval from 0 to infinity. It's not 0, it's not infinity, it's some positive number in between there. Okay, so we have a set of terms which are positive, and you have a quotient that has a limit as n approaches infinity of L. That L is some number that is between 0 and infinity. Not 0, not infinity, but somewhere in between. If that's the case, the sum as n goes from 1 to infinity of a sub n and the sum as n goes from 1 to infinity of b sub n both converge or both diverge. So this allows us to compare our limit, this allows us to compare not our series, but the limits of the nth term of our series, or rather the limit of the quotient of the nth terms. Here we can use this previous series as a nice example of how to use the limit comparison test. So, example. Does this series converge? We're going to take the sum as n goes from 0 to infinity of 4 to the power n over 5 to the power n minus 6. And here, we're going to try to compare it to 4 to the n over 5 to the n. The limit comparison test and the direct comparison test, you're going to compare to the same thing. It's just the way you're going to compare is going to be done differently. All right, so what we're going to do is we're going to take, here's our nth term of the series that we're studying. Now, let's consider the nth term of the series that we wish this was, and let's divide them. So this is 4 to the power n over 5 to the power n minus 6. And we're going to divide that by 4 to the power n over 5 to the power n. Okay, and now we're going to take the limit as n approaches infinity, just like this. Well, back in Cal 1, we know that taking limits is complicated, so we simplify this expression by just using some basic algebra. Algebra is simpler than calculus, yeah? So here we can write, well, it can be, it doesn't always have to be. Here, let's take the limit as n approaches infinity of 4 to the power n over 5n minus 6 times the reciprocal, which is 5 to the power n over 4n, just like that. Now here, these two numbers divide away, which give us 1. And so now we're left with a simpler limit, which is the limit as n approaches infinity of 5 to the power n over 5 to the power n minus 6. If we're back in Calculus 1, we can now say divide the top and bottom by 5 to the power n. Divide top by 5 to the power n, divide bottom by 5 to the power n, and that would give you the limit of 1 over 1 minus 6 over 5 to the power n. And then that limit can be evaluated nicely. If we're in Cal 2, which we are, we could also use L'Hopital's rule. After all, this is an indeterminate form, infinite over infinite. Taking the derivative of the top and bottom will also give us our result. Either way, this limit is equal to 1. And again, you could either divide top and bottom by 5 to the power n, or use L'Hopital's rule, and either way we get our result. But now notice the limit of these two quotients, the limit of these two quotients is equal to 1. Oh, so then by the limit comparison test, that means our sum behaves like the sum as n goes from 1 to infinity of 4 to the n over 5 to the n. All right? Here's the nth term of our series. Here's the nth term of the series that our series will end up behaving like. Oh, in other words, our series will behave like this series, which converges, which is a convergent geometric series. Which means that our series, the one we care about, the one we're looking for, will also converge just like this geometric series. Note here, the important part was that this limit was equal to 1. It didn't have to be 1. It could have been 10 or 45,000. All that matters is that this number be finite and not 0. Just like that. And seeing that again, let's see what happens if you take the series, and here again the question is, does this converge? We're going to take the sum as n goes from 1 up to infinity of, we're going to take 5 over n squared times n plus 4. Okay. Once again, we want to, whether we're using the direct comparison test or the limit comparison test, we want to go ahead and find something to compare this to. All right, well, the simplest form of this, I have a constant on the top and I have a cubic on the bottom. This is n to the third plus 4n squared. The simplest thing that I can think of that sounds like that, constant on the top and cubic on the bottom, is 1 over n to the third. So let me go ahead and compare that. I'm going to take my terms and I'm going to compare that to 1 over n to the third. They have the same form, meaning constant on top, cubic on the bottom. So now let's take the limit as n approaches infinity of this thing. Okay, well, that's going to be the limit as n approaches infinity. Let me leave that alone. 5 over n squared times n plus 4 times, we're going to multiply by the reciprocal here, n to the third over n to the third over 1, just like this. Now I can go ahead and multiply out the numerator and the denominator. So this will give me the limit as n approaches infinity. That numerator, 5 times n to the third, is 5n to the third. The denominator would be n to the third plus 4n squared, just like that. And now, again, if we're in Cal 1, we could take this limit by dividing top and bottom by the most dominating term, the term with the biggest power, n to the third. So if you divide top and bottom by n to the third, you get your result. Or if you prefer to use the Cal 2 technique, you can use L'Hopital's rule on this. After all, this is of the form infinity over infinity, which is a candidate for using L'Hopital's rule. In any event, here we get a limit of, maybe pause the video and try it and see what you get. And once you get your limit, go ahead and unpause and we'll see what the answer is. Yeah, and the answer is 5. So here we have a limit as n approaches infinity of the nth term of our series divided by the nth term of a much nicer series, one that we know things about. And here, this is the number 5. Now, that number 5 doesn't actually matter. All that matters is that this is finite and not 0. Incidentally, if this is 0, then the test fails. If this is not finite, if it's infinite, the test fails. That doesn't mean that we found that something converged. It doesn't mean that we found something diverged. It just means we have no idea. So here, this must be finite and not 0. If this is infinite or if this is 0, we don't learn anything about the series. But since this is finite and not 0, that means that by the limit comparison test, our series will, well, we know this will converge, the sums of 1 over n to the third, so that means we know our series will converge. By comparing to the sum as n goes from 1 to infinity of 1 over n to the third, which is a p-series, with p equal to 3, which is greater than 1. So we didn't know anything about our series, but we knew that if we took the nth term of our series and divided it by the nth term of this p-series, our limit would be finite and not 0. Oh, that means that our series will behave like this p-series down here. And since this p-series converges, that must mean that r-series converges as well. And that brings us to the end of the section. So that is it for the comparison test, both the direct and the limit comparison test. For an assignment, go ahead and try section 9.4. Do problems 5 through 33 odd. And that is it for our section. I hope you all have a nice day.